Okay, so to continue our discussion of valence shell electron pair repulsion theory, in this video we're going to talk about the effect of lone pairs on the final shape of a molecule. We know that there are 5 basic arrangements that we've discussed, depending on 5 basic geometries, depending on the number of electron pairs around the central atom. We didn't discuss whether those needed to be bonding pairs, lone pairs, how do we treat double bonds and triple bonds. So we're going to start, though, by just a quick review of the geometries dictated by a few of the numbers of electron pairs that can be around the central atom. For 2 electron pairs, we get a linear geometry. So in other words, those electron pairs, in trying to move as far away from each other as possible, will arrange themselves 180 degrees apart. And in fact, those 2 lines can represent lone pairs, single bonds, double bonds, or even triple bonds. So for instance, in a molecule like CO2, which is this, these double bonds count only one time. So in other words, each one counts as a single electron pair. So we would count 2 electron pairs on the central atom, and thus CO2 as a linear molecule. It doesn't matter that there are 2 bonds. The double bonds sort of come as a combo. So they can't move apart from each other. So they're counted just one time each. For 3 electron pairs around the central atom, they arrange themselves 120 degrees apart, and it was called a trigonal planar geometry. So this is an arrangement. Those are all on the plane of the screen, so in the same plane, 120 degrees apart. For 4 electron pairs, they arrange themselves 109.5 degrees. This is the furthest part. Now remember that the wedged line is coming out of the screen, the dashed line going back into the screen, and the 2 just sort of regular lines are in the plane of the screen. This results in sort of a pyramid type shape with a trigonal base. Trigonal bipyramid is achieved when we have 5 electron pairs around the central atom. That looks like this. 2 types of bond angles in this structure. Okay, 90 degrees between the electron pairs in the axial position to the electron pairs in the trigonal sort of middle or base or sandwich part of this bipyramid, and then 120 degrees between the electron pairs within that trigonal plane. So these are the basic geometries. I've left off the example of 6 electron pairs, the octahedral arrangement, just because I didn't have room on the screen. But we will come back to that in just a little while. Now again, as I mentioned, these lines that I've drawn can represent single bonds, double bonds, or lone pairs. And what we'd like to look at is how the lone pairs actually affect the final shape of the molecule. So we're going to start with the trigonal planar example. If you have a molecule with no lone pairs, then all of those lines represent bonds. And the final shape is just the same as the arrangement of the electron pairs, the electron pair geometry. And so it's just trigonal planar. It looks like this. And so our shape is called, in fact, trigonal planar for that, for this particular arrangement. If you have one set of lone pairs, though, those lone pairs are going to occupy one of the positions in that trigonal plane. So we'll remove those and put the lone pairs in. Now, the 2 remaining bonds, which are right here, right, the 2 bonds that are shown, will not move positions right? They're not going to move up into a linear arrangement because the electron density, the negative charge from the lone pairs, is still occupying that space. So there would be electron-electron repulsion that keeps those from moving over. The result is that you have this sort of bent molecule, and in fact that's what it's called. The shape of this molecule with 120 degree bond angles is called bent. So one lone pair out of the trigonal planar, or when we have 3 electron pairs and one lone pair, you end up with this particular shape. So you can see there's sort of two categories of the trigonal planar arrangement. With 0 lone pairs, you end up with a shape which is called trigonal planar. So all those lines represent bonds. And then if one of those positions is a lone pair, then now the molecule is called bent. The shape is dictated by the positions of the atoms. But of course, the positions of the atoms are dictated by how the electron pairs, including lone pairs, are arranged around the central atom. In this case, 120 degrees apart. So in the tetrahedral case, if there are 0 lone pairs, so each one of these lines represents a bond to an atom, they're going to arrange themselves, of course, 109.5 degrees apart. The shape is called tetrahedral. Now, if you have one of those positions as a lone pair around the central atom, so what I'm going to do is draw out the tetrahedral arrangement. So each of those lines is going to end up representing a pair of electrons. If one of those is a lone pair, though, that is going to prevent the 3 bonds from moving up into a trigonal planar shape. So those are going to, based on valence shell electron pair repulsion theory, since those electrons in the lone pair are negatively charged, they are going to occupy space. And so we still count this as 4 electron pairs around the central atom, arranged in 109.5 degrees apart. But the final shape, since the shape is dictated by the positions of the atoms, looks like a little pyramid like this. Okay, sort of a shorter pyramid than the tetrahedral. We call this, in fact, to distinguish it, a trigonal pyramid. If there are 2 lone pairs around the central atom, now 2 of these positions are going to be occupied by lone pairs. We have 4 total electron pairs. 2 of those lines we need to make lone pairs, like this. And I'm just putting these little gray lines in to represent where where those positions were previously, so you can see them a little easier in terms of their arrangement. Those electron densities look like that. They're going to remain, because the lone pairs have negative charge, that they will arrange themselves along with the bonds around 109.5 degrees apart, and this shape is called bent. Now, to distinguish it from our bent structure with the trigonal planar geometry, we'll write in the bond angle, which is 109.5. So we have 2 types of bent structure. So one thing that you might notice is that if you start with just counting up electrons around the central atom, electron pairs, for instance in this bent molecule we just drew, you have 4, and then you draw the tetrahedral arrangement of those 4 pairs. Once you fill in atoms in lone pairs, the molecule looks bent. It looks like its name. And so it's pretty easy, just first starting out with arranging your electron pairs into one of these, 4 basic geometries, 5 if we move on to 6 electron pairs. It's pretty easy to remember the name, because the names sort of look like, or the names describe them pretty well, right? Tetrahedral arrangement with 1 electron pair, the shape looks like a trigonal pyramid. Okay? In tetrahedral with 2 electron pairs, the shape looks like a bent structure once you're done drawing it. So that sort of helps you remember what the name of the shape is. Let's move on to trigonal bipyramid. This one's a little tougher because there's a lot more variation depending on the number of lone pairs, and we can have more lone pairs around the central atom in this case. If there's 0 lone pairs, then the shape matches the arrangement of the electrons. So every one of these lines represents a bond, and we have a trigonal bipyramid shape, which I'm abbreviating here TBP. If you have 1 lone pair, we now have to decide which position is best to put that lone pair in. Now lone pairs, since they're a little more diffuse, they're not confined between 2 atoms, we characterize them as occupying more space. So the lone pairs we're going to put them in a position in that trigonal bipyramid arrangement which gives them the most space, which is going to be in the plane, the trigonal plane. So since we have a 90-degree angle between electron pairs in the axial, the up and down positions, to the trigonal plane positions, but a bigger angle, 120 degrees, between electrons that are in the trigonal plane, the trigonal plane has a little more room. And so we'll put the lone pairs in that position. And this is kind of an interesting structure. If you imagine this tilted over to the right on its side, it looks like a seesaw. If you have 2 lone pairs, again, those lone pairs are going to be added into the trigonal plane. So we'll remove one of those, put in lone pair. Now you have, again, if you sort of manage rotating this around, it looks like a T, and we call this T-shaped. And then finally, for 3 lone pairs, you're again going to put the electron pair, the third one, in the trigonal plane, right there. Okay, and the orange represents those electron densities. Notice, these are still occupying space and still negatively charged, so they are affecting the shape of the molecule. And the final shape for this one, a trigonal bipyramid arrangement of electrons with 3 lone pairs, ends up in a final shape which is linear. And so this is these are the possibilities then for 5 electron pairs around a central atom. We have 4 different shapes depending on the number of lone pairs. And again, you can start, when you draw your Lewis structure, simply remember how to draw the trigonal bipyramid arrangement. Once you fill in the atoms and the electrons at the end of those within the structure, the final shape sort of looks like its name: seesaw, T-shaped, and linear. And that makes it a little easier to remember. Now let's do octahedral. So octahedral has this arrangement. If we have 6 electron pairs, right, they arrange them 90 degrees apart. 0 lone pairs ends up that each of those lines represents a bond, and we call the shape octahedral. So the shape matches the electron pair geometry. If you add 1 lone pair into that structure, in this case, since each of those positions is equivalent, all are 90 degrees apart, it doesn't matter where you put the lone pair. I usually put it in this bottom position to start. So the lone pair, there are 1 lone pair is in the bottom position, and now what the shape is called, and what it looks like, in fact, is a pyramid with a square base, and so we call this a square pyramid. And then next, for 2 lone pairs, now we actually do have a choice of where to put the second set. right? So if we put the first set of electrons in the lone pair in the bottom position here, then we can either put the second pair of electrons, in one of the positions in the plane, in the square plane, or in the position that's going up. Now, since we mentioned before that lone pairs like to have a little more room, if I put it in one of the positions in the square plane, in the base of this pyramid, then that would result in 90-degree angles between the two lone pairs. Right? But if I put them in the up position on the opposite side, now those electron pairs are 180 degrees apart, which is a little more stable. So in general, with 2 lone pairs, out of our 6 total electron pairs on the central atom, they'll arrange themselves in the top and bottom positions, 180 degrees apart. And this particular arrangement is called square planar. Again, the shape looks like the name. Okay, so they're pretty aptly named and easy to remember. So this is how the lone pairs of electrons affect the shapes of molecules for electron pairs 2 through 6 around the central atom. And we will go on to some example cases next.